Hi folks, we're going to take a look at number 10a from page 213. So they ask us to find the horizontal asymptote of this function here. And so this is a little different from most of the functions that are quotients, which we've seen, but is very similar to a question that was in the lesson. So the idea here is, while this is not a rational function, because the denominator is not a polynomial, it looks a lot like a rational function. And the idea is that if I look at the denominator function, I've got a quadratic, but it's being squared. So I would expect this function in the denominator to behave like a linear. But if this one behaves like a linear, and the numerator is also linear, well, they behave like polynomials of the same degree. So I would expect to have a horizontal asymptote. So the question is how to determine it and how to justify it, because this is not something that we established in a more general case. And we're going to do the same thing we did when we established the general case of the end behavior of a rational function where the degrees are the same, is I'm going to divide numerator and denominator by the highest power of x. Now this is where you have to be careful, because in this denominator, the highest power of x is not x squared, because remember, it's being square rooted, and the square root of x squared is just x. So that's the first thing we're going to do. All right, is we're going to take the limit as x approaches. Now in this case here, this is going to work for both positive and negative infinity, because while I have a square root here, I see that the x values are being squared. So this is always greater than or equal to 0, and then I'm adding 1. Okay, so what's inside the square root is always strictly positive. All right. If it wasn't, I'd have to consider perhaps that it only existed to positive infinity or negative infinity. So here, this is actually going to work for both positive and negative infinity. And what I'm going to do here is, like I said, divide numerator and denominator by the highest power of x. So divide the numerator by x and divide the denominator by x. All right. Now the numerator works great because x over x is just 1. It's the denominator where we have to use a little bit of cleverness, is I'm going to rewrite x as the square root of x squared. Okay. Now, if I rewrite this as the square root of x squared, normally I wouldn't show this step, but I'll show it here. So I have x squared plus 1, and I'm rewriting x as the square root of x squared. I can now use my properties of radicals to bring this division all under 1 square root. All right, so now we've got limit as x approaches positive or negative infinity of 1 over, okay, and this will just become x squared plus 1 divided by x squared. So this is just properties of radicals. Excuse me, and now I can do the simplification. So at this step here, there was no simplification I could do, but now I can. So limit as x approaches positive or negative infinity of 1 over, and what do we have left inside the square root? Well, we just have 1 plus 1 over x squared. All right? And so what happens, excuse me again, is as x gets very large or very, very small, this expression approaches 0. So the whole thing just approaches 1 over the square root of 1, which of course is just equal to 1. So that means that the horizontal asymptote is just given by y equals 1. Okay, so just to recap here, is while this was not a rational function, I used a similar trick that I used when I had a rational function where the degree was the same in the numerator and the denominator. So in this case here, the highest power of x was x, divided numerator and denominator by that, and here I had to use my properties of radicals to bring this x inside the square root by rewriting it as square root of x squared. Okay, that's it for this one.